Ralf Schlüter, I guess, is the backup. Let's see if it works.
Hello, my name is Wei Zhou. Welcome to the talk of acoustic data-driven subword modeling for end-to-end speech recognition. This is a joint work with Mohammad Zainaldin, Zuo Yunzhen, Ralf Schlüter, and Hermann Ney. The talk will be arranged in the following: introduction, the proposed acoustic data-driven subword modeling approach, experiments, and conclusion. End-to-end automatic speech recognition has achieved great simplicity and state-of-the-art performance. Subword units are the most common label units for such systems. Popular text-based subword modeling approaches include byte pair encoding, word piece model, and unigram language model approach. Both BPE and WPM leads to deterministic segmentation of words. The major idea is to merge pairs of units based on certain criterion. On the other hand, the ULM approach leads to probabilistic segmentation. It adopts iterative vocabulary refinement and model training in an EM algorithm. The trained ULM also supports subword regularization later by drawing samples of segmentation variants in subsequent tasks. However, as purely text-based approach, there is no consideration of the underlying acoustic signal, which is the key of ASR. While automatic label learning from an acoustic perspective has been well studied for the classical ASR systems, it's not fully addressed in end-to-end ASR yet. Existing acoustic-based subword methods include the following. The pronunciation-assisted subword modeling tries to explore the acoustic structure of subword units based on a pronunciation lexicon. The final labels are then obtained via some post-processing on a text corpus. However, no acoustic data is involved. Both the gram CTC and latent sequence decomposition approaches tries to utilize the acoustic data for subword sequence decomposition. The major idea is to improve the performance of ASR by exposing the model to various segmentations in training so that the model can jointly learn an acoustic-based sequence decomposition within a fixed vocabulary. And this vocabulary is usually taken from the most frequent n-gram characters in the transcription, which is also clear that neither approaches aims at a acoustic-oriented subword modeling. In this work, we propose acoustic data-driven subword modeling, in short ADSM, which is a fully acoustic-oriented label design and learning process. The approach combines most advantages of the aforementioned methods. It produces acoustic structured subword units and acoustic matched target sequence for further ASR training. Let vector A denote a sequence of subword A from a vocabulary V. We denote SW as the set of allowed segmentations of word W using this vocabulary. The initialization step of ADSM is based on a pronunciation lexicon, where we can obtain grapheme to phoneme pairs similar as PASM. The vocabulary is then initialized as all subword units from those G2P pairs. Most of them can be regarded as graphemic representation of phonemes, therefore they have a clear acoustic structure. SW is then defined as all possible segmentation of W using this vocabulary, which also largely relaxed the quality requirement of G2P alignment. We further discriminate subwords at word end to be a different label, as shown by the example here, since they might contain different acoustic property. This also allows an easy reconstruction of word. This discrimination is further carried out into V and SW. The next phase of ADSM is repeatable iteration. The first step is vocabulary refinement via model training. Given SW and V for each training utterance with acoustic feature sequence and corresponding word sequence, we denote SW as the set of allowed subword sequence for the full utterance. The model training objective is then given by the equation here, which is a marginalization over all sequencing SW. This can be regarded as an extended marginal likelihood in the ULM approach with further dependency on the acoustic input. This loss function can be further transformed into an extended CTC loss as done in the gram CTC approach. Here we have H1 to T as the encoding output with optional subsampling, Y1 to T is the blank augmented CTC alignment sequence, where the unique mapping to A is guaranteed by the CTC collapsing function, and the P' is defined over vocabulary plus blank. This loss function effectively computes a marginalization over all CTC alignments of all allowed subword decomposition of the utterance W. Therefore, by training with respect to this loss over the acoustic data, the model learns to converge to the most probable segmentation of each utterance in an acoustic data-driven manner. To obtain this most probable segmentation, we simply apply a Viterbi aligning with the trained model, as shown by the equation here. Here Q is the prior distribution estimated by marginalizing P' over the training data, and lambda is the prior scale which is used to control the smoothness of the overall model. Based on this forced alignment and some weight filtering, we can obtain the refined S tilde W and V tilde. For the weight filtering, it's simply done as the following. For each W, we gather all subword decomposition variants in the alignment together with their counts. We then normalize the counts to weight with respect to the occurrence of W. We filter out a sequence with weight less than threshold mu, and the remaining sequence forms the S tilde W, which also reveals V tilde. The next step of this iteration is subword merging. Recall that the major idea of BPE and WordPiece model is to merge subword units based on certain criterion. This can avoid too long sequence with many small units, which can be beneficial for spelling and context dependency modeling. We also adopt subword merging into ADSM to enhance S tilde W and V tilde. For each sequencing S tilde W, we merge any two neighboring units to form all possible sequences, as shown by the example here. This creates new labels into V tilde and new sequences into S tilde W, where the original sequence is always kept. Note that since all the labels before merging has a clear acoustic structure, the merged units also retain those acoustic structure. Finally, with the enhanced S tilde W and V tilde, we can repeat the iteration to again learn labels in an acoustic data-driven manner. For the subsequent vocabulary refinement, we increase the subsampling factor in the encoder by 2 to encourage the model to learn larger units. The finalization step of ADSM is done with one last vocabulary refinement plus a word count filtering to obtain the S final and V final. For the word count filtering, if a word occurs less than k times, we only take its single best segmentation based on weights. The final vocabulary size is then controlled by the prior scale, weight filtering, and word count filtering jointly. The obtained final vocabulary then reveals the acoustic structured ADSM labels. Also, the final forced alignment gives the acoustic matched target sequence for further ASR training. This can be regarded as acoustically most probable decomposition of each utterance. In the table here, we show some simple example of the output of each aforementioned ADSM step. We have initialization, refined vocab, subword merging, and refine again. Text segmentation without audio can be needed for training subword language model on extra text data. This can be simply done in ADSM. For words in S-final, we can simply draw samples of segmentations based on weights. For words not in S-final, we can train a simple n-gram language model on the S-final, and based on this model, we can pick the best score segmentation among all possible variants within the vocabulary, where the statistics are then more from acoustic preference. Experimental verification is done on the 960-hour LibreSpeech corpus. The ADSM initialization is done on the official LibreSpeech lexicon. For each vocabulary refinement step, we train the model for 25 full epochs, which can be done in about 1 week on a single GTX 1080 GPU. We use those prior scale weight filtering and word count filtering values throughout the experiments. We apply one iteration plus finalization to obtain 5K ADSM labels. Here in the table, we show some statistics of each intermediate step. These include the vocabulary size, the average number of segmentation variants per word, and the average length of all subword sequence in the complete SW. We see a clear reduction of these two terms before and after each vocab refinement step, which indicates the model's convergence towards specific acoustic probable decomposition. We also see a clear decreasing of the average sequence length, which indicates that the model learns larger units. For comparison, we also generate 5K BPE and 5K PASM, whose average sequence length is 3.2 and 5.7 respectively, versus the 4.7 here. We see that PASM without any merging operation has the longest sequence length. For reference, the average phoneme pronunciation length is 6.5. All three subwords are further evaluated on different end-to-end ASR approaches. We follow those work to train CTC, monotonic RNT, and LSTM-based attention models. The word error rate without external language model are shown in the table here. We see that ADSM clearly outperforms both BPE and PASM in all cases. The most significant improvement is obtained for the RNT. We see that both acoustic-based subwords outperform BPE, which indicates the benefit of acoustic structure for such time-synchronous model. The difference becomes smaller for the attention model, where the context dependency becomes jointly important for the attention mechanism. Here, BPE as a text-based approach has a clear advantage, whereas PASM seems to suffer the much longer output sequence length. On the other hand, ADSM with the merging operation has an acoustically more balanced sequence length, therefore is suitable for both time-synchronous and label-synchronous models. Here we also show some segmentation examples of the three subword approaches. We see that ADSM achieves acoustically more logical segmentation. To further illustrate the importance of both acoustic structure and label size, we conduct some analysis experiment using the subword CTC plus a foreground word-level language model. This leads to an idealized context modeling, as the spelling is perfectly defined in the dictionary and the cross-word context is captured by the word LM. We see that both acoustic-based subwords, PASM and ADSM, become similarly good and outperform BPE, which indicates the benefit of acoustic structure of labels. On the other hand, when removing such an idealized context modeling, PASM has the most degradation. Recall that PASM without any merging operation has the longest sequence length. Therefore, this also partially justifies the disadvantage of too long sequence lengths for end-to-end ASR. In conclusion, in this work we presented ADSM, a fully acoustic-oriented subword modeling approach. The complete procedure of label-designed learning is acoustic-based, which is more consistent with ASR. It combines the advantages of several subword methods into one pipeline. It produces acoustic-structured subword units, as well as acoustic-matched target sequence for further ASR training. The obtained ADSM labels are further evaluated for different end-to-end ASR approaches on the LibreSpeech corpus. These include CTC, RNT, and attention models. And the ADSM clearly outperform both BPE and PASM in all cases. ADSM achieves acoustically more logical segmentation, as well as acoustically more balanced sequence length, therefore is suitable for both time-synchronous and label-synchronous models. Thank you for your attention.
Could we
first to turn it on.
online?
Hello.
Oh, wonderful.
Hi.
Hi, Wei.
Hi.
Okay, so do we have questions here in the audience? Okay. You want to ask a question?
Okay.
Oh, there it is. Can you come to the front, to the microphone and to the camera?
Thanks for your talk. I guess I missed something. If you produce, if you have a bottom-up procedure for constructing symbolic representations for the audio, then I can understand that you, at a certain moment, you need a lot of constraints to get grip on that procedure. But what I don't understand is, what I missed maybe, is how you then relate your resulting collection of symbolic units with an LM that comes from text. So I guess I missed the relation between the bottom-up symbolic units on the one hand and the orthographies that you need from the LM side. So is there anything to say? Do I miss something?
I'm not sure if I understand you correctly. Do you mean the segmentation of unseen text?
Well, at the moment you talk about the bottom-up construction of acoustically meaningful set of units from the audio. Huh?
Right. And this was initialized based on the G2P pairs, where you have all the labels from the G2P pairs, and
okay.
all of them are regarded as acoustic representation.
Yeah. There's a G2P there.
Yeah.
Okay, thanks. Yeah, that's also what I missed. Sorry.
Okay, so do you have more questions in the audience or remarks? Oh, Katja.
Maybe I missed something, just a quick one. So when you show that your units are superior to BPs, in that comparison, do you have the same amount of your units and BPs when you compare?
Right. All of them are 5K size.
Okay, so it's the same amount, it's just different splitting. Okay,
Right.
Thank you.
You're welcome.
So do we have more questions? So maybe I will ask one. When I read the article, this evoked me the clustering of acoustic units in classical systems like the context-dependent units and so on. Can you compare your approach and the approaches that were used before in classical systems? Or if you see some advantages or disadvantages?
Actually, they might come in the similar origin. So for the classical ASR systems, the label units are also learned in kind of an EM algorithms, which is done similarly as we do by marginalizing over all possible segmentation within this given seed vocabulary and iteratively to refine that. This is quite similar in the classical way, which I cited in the slides. I think it's the PhD thesis of Michael Piccini, I think so. Yeah.
Okay, and you are adding the merging, so I think that this is not in the classical system.
Right. Sorry. Yeah, I should mention that as well. The merging is necessary here, as I pointed later, for to reduce the length of the sequence and to have sort of larger units, so that the model has less difficulty to learn the spelling and context modeling. This is not the case for classical ASR, since you have the lexicon, and phoneme mapping to words are perfectly given, so you do not need to worry about such the spelling and those cases. Therefore, it's done differently here. Thanks for the question. It's very
thank you very much. So do we have more question?
An online. Yeah, we got one. Okay, so the question is from Andrei Andrusenko. Do you have any comparison with graphemes?
What kind of graphemes?
I think that means by just using a letter as a unit.
Okay, if it's comparing the single character, yeah. I would say it will always be worse. I think it's already shown in many public literature that the single character is worse than BP and other subword-based approaches due to the difficult, as I mentioned, for the spelling, for the context modeling, and in that sense. Therefore, I do not have the results in this paper, but I could imagine this would be worse. Yes.
Okay, I think we have to move on.
Yes, thank you for your contribution, and we will move to the next speaker.
Let's thank the speaker again.
Thank you.